Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to show you an example of inspecting a thin wall thermal well with a pressure tab, which is a common piece with a very thin wall that needs to be inspected by immersion testing. We want to use this example to show you some of the features in BeamTool, such as drawing a custom piece by importing an image, and then on top how to change the setting in the conventional probe set to do a immersion testing. Okay, so for doing that, first step, now that we want to draw a custom piece, is that we can go to piece section and select custom. Here, when we do that, the first thing that we have here is set is the velocities. We know that the piece that we, in this example, we're going to inspect, going to be from steel, so we are good with the velocities. Otherwise, we can change the velocity directly in this tab. Now, you notice that because we have a custom piece, there is no default geometry drawing in our workspace. We can easily start to do a drawing by using these geometry lines, or in this case, we have an image that can help us to do the piece drawing. So I can come here and say File and say Import and come to Image, and then I can choose an image, which is the image of that thermal well as a drawing with some dimensions on it. So this image has come from the official engineering drawing, so the aspect ratio is 1:1, and I have a dimensions specifically on that. So here we have a section, the diameter to be 26.67, this length is 72.84, and this tiny thickness that you want to inspect is 1.38. And the drawing is made to make a cal block, so you can see that there are some notches were simulated on the surface of this thermal well. So basically the idea is that we design a technique that can the sound go through this thin section and then this thicker section, and be sensitive in detecting any essential surface defect or surface breathings that is simulated by notches here. Okay, so the first thing is obviously we need to do a drawing, prepare a drawing of this piece that needs to be to its scale. And this is where we can use a very neat tool in BeamTool, which is interactive scaling. If you click on this image and come down to where you see this wrench shape icon, and we click on that, you have some very, very important and handy tools. The first one that I want to use here is interactive scale. The interactive scale tool is going to help us to automatically rescale and resize the image to match its original dimensions. So here, when I click interactive scale, my cursor turns into a measuring tool, and I can use one side with a known measurement as a reference. So here, I know from this point to this point, the dimension is supposed to be 26.67. So what I can do, I can zoom in this location and one click on the corner here, and now is where I see the measurement tool, and then unzoom and zoom here again, and come here and click on the other side. So what currently this distance is 40.92, but we notice that we want it to be 26.67. So when I do this and say scale geometry, now what's going to happen is that the image is scaled to be this length to be around 26.67, and we can basically double check that. But before I do that, the next thing that is useful to do is to set this image from one reference of choice to the origin of our whole workspace. And that's another tool here that I can come here and say move drawing to origin. If I click move drawing to origin, then I can come and choose which corner or which location this image I want to go to origin, which is 0, 0. And in this case, I want to choose this corner. So if I click on this corner, Now you notice that this corner is automatically moved to 0, 0. So by using interactive scale and move drawing to origin, now I have a drawing that one corner of my choice is 0 to 0, and the dimensions should be exactly or very close to a drawing. And here now you can notice that since this corner has 0, 0, if you zoom here and look here, you would see that exactly this corner is past 26. And if you go around it, that's to 26.6, which is pretty close. Or same here, you can notice that if we zoom to this corner, it is somewhere past 72, so to be exact, around 70.7, which is very close to 72.8, depending on where exactly you move your cursor or put your cursor. So now that we have our geometry loaded properly, like the image is properly and there with the correct scaling, correct dimension, we need to create the actual geometry that we want to use to interact with the beams when we add a probe. Here, then we can use this geometry tool here. So here, if we move on this one, which is a polygon drawing, can click on polygon, and now since the actual piece image is there, we can just use it as a reference to draw on. So I can come here to this corner, click, and now move and choose the second click, then come down here, then move here. And since this is like a rotation piece that can be rotated, I can just only draw a top section. So I come here and then I just follow the trace on this image, do different clicks and move these lines. Next point, all the way till back. And now I have my geometry drawn. So you can notice the geometry that if I can now click on my image and move my image down, you see that now I have a trace of the actual section that I want to inspect. I can either leave this image underneath or I can move it. And for now, I'm going to just move it on the side for a second. Now, what I need to do right now is to add a probe. I want to do the inspection of this piece because very thin wall in an immersion setting. So in a conventional mode. So I come here and choose conventional UT. And as a default, BeamTool will add a conventional probe with a conventional wedge at the location that the beam offset is 40 millimeters from the origin. Now, if I go to the probe configuration, the first thing I want to do is to tell BeamTool that I want to use immersion setting. That's the interface between the probe and the piece. So I can come here on the wedge configuration section. And if I click on this wedge, now you see that I will have options. The default is a block wedge that it's already the transducer is located on. I'm not going to use contact in this case because I want to do shear refraction. So I choose immersion. When I choose immersion, the first thing that you notice is that now the wedge is gone and you only have a probe with a normal to the probe indicating a 0 degree or the beam normal to the face of the probe. Also, another thing that is important is in the immersion, currently by default the velocity is put to 1.48, which is a default compression velocity for water. If this is immersion, our immersion system is in different material or different velocity, that's what we can directly use here. But for now, I'm just gonna use a regular water with the velocity of 1.48 millimeter per microsecond. Okay, now as a default also the beam that is chosen is in a shear mode. Obviously right now it has no effect because we are shooting 0 degree anyways, but as we move the probe on the side and start tilting, then choice of the mode is important. So here the first thing I do, I'm going to move my probe, and at this point you notice that as soon as we go to the location that the beam can actually interfere with the piece, you will see that the beam enters the piece and you have by default a beam spread on. And here you notice that the choice that is made is shear and you see a beam spread. So Next step that I want to do is to come to the section that is a thin wall or 1.38 millimeter. And now I want to create a shear beam. Here, the choice of creating shear beam would be by tilting the angle of the probe such that the intersection, the incidence with the surface be on angle. So then because of the velocity difference in my piece and in the water, I can refract the beam inside. So here I can do that by just using this basically rotation angle here. And you notice that as I rotate this, now you'll start to see a refraction inside, which now you know that it is a shear because the shear mode is selected here. But if you wanted to, for another application, for instance, create compression, you could just create compression. And obviously then our angle that we wanted to use needed to be below the critical angle below the critical angle. But here, since I want shear, I can choose shear. But the next question is, what would be the best angle? We know that if we treat all the surface breaking stuff as like sharp indications like notches, as drawn in this cal piece, we know that typically some angles between 35 to 58 would best be to interact with corners and see those kind of sudden changes in the surface. So if I want to set a goal that my refraction angle be 45, I can use this tool here that shows the Snell's law. When I turn this on, what it shows, it's going to track what angle the beam is creating with my surface of the piece, and then based on that, and based on using the velocity of the water which is set and the velocity of the piece that we identified before, it's gonna tell us what angle is actually being refracted. And in this case right now, with my tilt of 12 degree in water, I'm creating a shear beam of 27.4 degree. So here what I want to do, because I want to get close to those range of angles we just talked about, I can just increase the tilt until I see that the Snell's law tell me something close to 45 degree. So here, if I have 19 degree rotation with respect to Z, seems like based on this calculation Snell's law, I get 45.85 refraction angle in the piece, which will be ideal. Now that my angle is fixed and my rotation angle is fixed, I can turn off the Snell's law. And the next point would be, where should this probe sit with respect to the surface? And the point that is helpful here is a near field tool. If I come here and turn on the display near field, you see these small dashed green squares along the beam that basically show you the extent of the near field. We know that the near field is related to the frequency of the probe and the diameter and also velocity of environment. In fact, if we go to this icon here, we have all the help menus in BeamTool that tell us what relationships are used to calculate this near field for display, or same for beam spread. And here, as known, the near field has a direct correlation with the square of the size of a probe or diameter of the probe, and also the direct relation with frequency and reverse relationship with the velocity. Okay, so now here the default probe is 5 megahertz and 10 millimeter diameter. So typically, again, because this is a very thin piece and we can see small changes in the ID, we want to use the higher frequency probe. So here, if I just choose to be a 10 megahertz probe, you notice that has changed that my beam spread changed. So before it was 5, so you see it was larger beam spread, and now that I have to higher frequency, my beam spread increases. But then I want to make sure that I put my end of my near field exactly at the surface that beam want to enter the piece to get a much more stable result. So the only thing I can do, my angle is fixed, so I'm not going to rotate the probe, but what I can do is to move the probe or shift the probe up or in another word, further from the surface in my immersion tank, let's say. How can I do that? I can do that by, again, use this positional, and as I move this, preserving the refraction angle. You see that if I keep moving up and up, essentially, what I'm looking at is to make sure that when my beam hits this surface, that would be the extent of the near field. To help with that, I can deliberately choose a probe diameter that actually shorten my near field also. So for instance, instead of diameter of 10, I can go to diameter of 6. And now, if I keep moving up my probe, you see there is now a point, there is a height, let's say now around 49 millimeter from the center of my probe and surface, that now my near field is exactly on top of a surface, and near field do not extend beyond. This comes with the expense. When I change the diameter, it comes with the expense of increasing the beam spread slightly, but there is a balance because these things are tied into each other. We change the frequency and diameter, it both affect beam spread and near field. In this case, I chose my near field to be the main criteria, to be right on top of the OD surface. Now, just to you realize, if I now bring back the diameter back to larger diameters, obviously the near field gonna be extend further and the beam spread become narrower. But I go back to my choice of 6 millimeter, and that's the spot that put my near field right on the surface. So at this point, this will be a technique that I'm willing to finalize. I can bring back the image right on top of where it was for presentation. And what you will notice is our setup in immersion tank would be to locate a piece at a certain reference point, and then with respect to normal to that, tilt the probe by 19 degrees to create the shear angle of our choice, which was around 45 degrees, and then make sure position-wise the center of the probe with respect to surface of our zero surface, which would be this top surface, to be around 49 millimeter. And at that point, we know that we have a 45-degree shear beam with the near field right on the surface, and then we can design our immersion tank motion to just do the motion axially in this direction, and then rotate the piece at one full travel and be confident that we are creating a technique that is sensitive to finding notch-like or crack-like or interruption, defects or interruption in the 3D surface. I hope that this video was useful to you. Thank you.